All right, thank you very much. Basically, what I want to say first, first of all, thank you for the opportunity to see all the stuff that I've seen for the discussion that I had with you. That was really enlightening, and I learned I learned a lot. So, but you gave me a pretty hard time that I'm now having, have to give my talk on the last day of this meeting, because I was struggling all the time what I'm going to tell you, no, and I don't want to bore you with stuff, and I so constantly changed my slides here, and I hope I have not completely screwed up my talk now. So let's see where this goes. But as said, I want to talk a little bit about the perspective from a modeler, from a climate researcher on permafrost and its relationship to infrastructure, and a little bit give you the opportunity to see what we have done. Yes. Okay. All right. I give my very best to stay within these 15 minutes I have. So you see this image, that is the place where we've been. It's in Dead Horse in the oil fields. Bill Strieber can tell you exactly, I guess, where it is. This big facility here. And this is what I show people when I explain them infrastructure, permafrost interrelationship, because most of the people don't know actually that we have a lot of vulnerable, highly vulnerable infrastructure on permafrost. And this picture shows you exactly all what we think in terms of what the big problem is from a climate perspective. So we see this huge vulnerable infrastructure. And what I see as a permafrost teacher is here all over degrading permafrost, right? And from a climate researcher perspective, what I see is a landscape that will change within the coming decades drastically. So I see a lot of risk here. And this is what I basically would like to show you a little bit what we do in this direction. Next slide, please. Well, as a modeler, we tend to oversimplify things. That's what I'm used to do. So we try to simplify it to a certain degree that we can handle it with our climate modeling approaches. And that's kind of the simple comic strip that we have in mind when we talk about critical infrastructure. And I also learned critical infrastructure, just using the word is also wrong, as just using kind of things like permafrost and thawing and all these kind of things. To give you a little bit of overview, what I see as critical infrastructure, how I define it, it might deviate from others people. So I see as critical infrastructure everything that is has a high socioeconomic relevance. So to be costly, it is important for society, it is culturally also important. So this goes all in there. I see critical infrastructure that is really relevant to the environment, so that poses a certain risk to the environment, so ecological risks. So everything that has to do with handling and storage of environmentally hazardous substances, for example, could be in there. Then, of course, the health impact. So you see these things go also together. They maybe go in one category, be in both, but that might be also critical infrastructure, and infrastructure, of course, relevant to security. That's the other thing. So this is kind of a compression, what is typically out there as in terms of the 16 types of critical infrastructure. So this is what I digest as a modeler from that. So you see here this comic strip, and that is what we think of. That's what I would like to talk most of in this talk here about industrial infrastructure, because here we see some of these boxes ticked basically. And if you do the next slide, then this is kind of the picture we have in mind, what happens to the infrastructure in the case of further permafrost degradation in the future. So some of this infrastructure, if we don't engineer it away in a way, or we're not able to engineer it away, a lot of this infrastructure is at risk to fail. And what happens then if we don't take care about what we brought in terms of substances to the infrastructure? It will kind of enter the ground at some point. It might be not hazardous, it might be hazardous, it might be mobile, not. So this is kind of not important to the current point, what we see, but we have this risk of there is infrastructure, there are hazardous substances, and we're running into a risk that we may contaminate the environment, and that causes other problems like health, water supply, and so on for local communities, for example. Next slide, please. That basically industrial activity and the accumulation of hazardous substances in the Arctic has something to do, shows a little bit this graph. So we have already seen in the talk from Bill, this crude oil production for Alaska, kind of the graph, that's the orange one in million barrels per day, basically. And we had this peak here in the 90s. And we see on the same side, this is now data from the Contaminated Sites program from Alaska, basically. We see how many contaminations were registered. And what we clearly see, it is not a surprise, and this is not rocket science, right? The more industrial activity, here now shown in terms of crude oil production, we have the more likelihood we have of contamination. That means we have brought in more hazardous substances that leak accidentally or intentionally. So that's the kind of things that we see. Next slide, please. We wanted to understand that now, not from a very detailed perspective. We talked about a lot of details here, individual sites. That's not what a climate modeler is doing. We try to bring that on the global scale, on the Arctic scale, and therefore we need data. And this is really complicated. We were inspired was maybe the wrong word, but there was this Norilsk event in 2020 with 17,000 tons of diesel just went into the tundra, and that kind of made us ask, okay, how big is basically the problem of hazardous substances already in the Arctic? And can we do something as modeler to at least point and scope the total potential a little bit? And that's what we did here. So we figured out that basically Alaska is having a great database on recording contamination as well as Canada. And we thought about, can we use that data to see if we can translate it also to other regions in the Arctic where we definitely have no data or no clue. This is mostly Russia, because those things are typically not recorded. And if they are recorded, we don't have access to the data. So that was kind of the idea. What you see on the map is basically a lot of red dots. Those are the industrial sites we have in Canada and Alaska. So we map them. We use different data products to get them. They are not complete, I have to say. That's a big problem. And you see then the contamination events in terms of green dots. Those were already cleaned up. So you see a lot of green, which is good. So obviously here's happening a lot of cleanup measurements. And you see the yellow dots, which are still considered active or kind of still under institutional control, which isn't 100% clear what it means, basically. So, but we make this to distinguish that. But we were not interested of how good the cleanup measurements are, but we were interested of how big is in principle the problem of industrial activities in the permafrost region. So we used the data, next slide please, in order to create kind of a simplified model. We investigated the spatial relationship between industrial sites. It's good because we know also in Russia where these industrial sites are, also in Greenland. And we investigated a little bit the spatial relationship. Basically, it's not big surprise there where we see a lot of industrial infrastructure, we see a lot of points of contaminations. And this gives us the opportunity to make a simple model and just do the relationship. This is called point process modeling. It's a probabilistic approach. And you see here now the reality in the black line. You see it's doing something here. It's the density of contaminations versus the density of infrastructure sites spatially. And you see our models, how they are lying or cutting through that curve. And you see basically model is not reality, reality is not model, but it gives us a little bit the upper and the lower scope, even though the curve goes out wildly here, but this is the best we can do at the moment. And we use that relationship in order to project it on the total scale, Arctic, Pan-Arctic scale, how much contaminations we would have or expect with the current industrial sites we see. If you go to next slide, then we see basically for Alaska, that's what the data tells us. We have 350 industrial sites. This is not individual infrastructure elements. These are considered larger complexes of infrastructure. And we are pretty sure we miss a lot because we don't have any data. We just have the open data available. We know that we have in the permafrost region about more than 1,000 contamination events already in Alaska. And if you use our model, basically which was tuned with Alaskan data and Canadian data, we see, okay, we get in this range also projected. And now we can do that for all the other missing countries, basically. And what we see is we're far beyond 10,000 of contaminated sites we have all over the Arctic. And this made us think, well, there could be a problem if we have these sites and permafrost is thawing on the long run, and we do not have access maybe in the future to the sites and we have to clean them up. Alaska and Canada is doing a good job in cleaning those sites up, but in Russia, maybe not. And yeah, well, this is now published in a study. We show also in the study how climate warming would affect those sites. Basically, when we go for the pessimistic climate scenario, all those sites will be soon, towards the end of 2100, located in actively degrading permafrost regions, so where we see thallic development in the model. Well, if you want to read it, this is the study that came out this year, and I think it's also on the USB stick. So next slide, please. shortly only about the data problem we have. You see here the combination of now the contaminated site program for that house. I pulled out that slide for that house. See all the points here. You see the infrastructure elements, and you see different combinations of data sets we used, and they are not necessarily matching each other. And that is a huge issue for us because we basically can do now the analysis from different data sets. And what comes out is that we most likely miss 40% of the existing infrastructure in the Arctic. That's highly likely. That means the picture that I showed you before is just like the tip of the iceberg, what we would say. It is definitely more out there, and we are working hard now to get much better data together to do the projections. Next slide, please. So from an environmental perspective, this is how now we further deal with the data. So this is now so larger permafrost region, not only continuous and discontinuous region, but also including the others. More points show up here. And what we do now is to understand how those contaminated sites are distributed and how they are located in watersheds, because the concentration of watersheds could be relevant to know in the terms we are not able to clean them up. And that's an analysis we do here. And what we see, it's also not rocket science. Watersheds get smaller and smaller the closer we get to the coast. And that it shows us here also, again, example for that house region, Prudhoe Bay region, that we have there the highest, let's say, hydrological, ecological problem maybe related to such sites if they occur. All right, next slide, please. This is now just work in progress a little bit. We try to build now models to understand and quantify a little bit better what does it mean when contaminations occur in such locations, hydrologically, and to the mobility of those infrastructures. Therefore, we use our models, and you see it's, again, very simplified. We want to understand if there is a contamination, how is that relate to the groundwater table, and how does this groundwater table link based on a slope, based on a distance to a water body, where these contaminants, if they occur, could be mobilized and maybe potentially contaminating a water reservoir or whatever. So this is an experimental work here. We try to do with this simple relationship an index that tells us something about this mobilization potential for contaminants and how this will change over time if we assume certain climate warming scenarios. And what you see basically is there where we have currently the lowest mobilization potential high up in the Arctic, where permafrost is very stable. It will or has already changed from 2010 to 2020 the most, and we expect also the most changes to occur there in the coming 50 to 100 years. Next slide, please. Now a little bit detour. We are not only doing these contamination things. This is kind of a side project, or it started as a side project. Initially, we started with looking at roads and infrastructure from a climate modeling perspective. So what a colleague of mine did, and Vlad was also involved. We took from this Dalton Highway section here, a little bit further south from Dead Horse, kind of data. And we used those data and the kind of construction details, and engineer would say this is completely stupid what we did, but this is how it looks in our model, right? It's very simplified, the structural elements and how we represent such structural elements in the model, basically. And we wanted to understand how does this basically, if we implement it in our climate model, how would the warming affect basically then kind of infrastructure elements individually, and can we assess something like a risk potential where we hit at some point or leave the margins, the security margins of, for example, the coarse gravel that we have here, the gravel bed, and when does the thawing or the talc formation occurs way beyond these construction details. Yes, next slide, please. This is how the modeling looks like. And as I say, this is very simplified. Don't consider that now a specific location, but just representative for general infrastructure and what we're doing on a long-term projection. And for us, it was lesson learned. How does permafrost thaw occurs at such infrastructure elements? Can we represent it with a model? And could we potentially then also go to other infrastructure elements? A road is pretty simple because it is a clear design, has clear design parameters more or less from our perspective, whereas other infrastructure is we have to find classes for that, infrastructure types represent those. So what you see in these results on our simulation, what we learn from those is basically, and I don't tell you anything new, the rims, here you see the road, here you see the road shoulder, here you see the open tundra. And what you see where this blob occurs after certain time periods, you see this is the most vulnerable part of the road are the shoulders. Nothing new to you, you know this all better than I do. But what we basically see is that we can, even in these cold permafrost environments, just a little bit south of Dead Horse, we create a pretty pronounced talc under the road if we just let the model run under the climate warming scenarios. And this is then leaving definitely your design parameters in a way that we get talc formation, constant permafrost thaw next to the road and creeping under the road. That means when we have, unfortunately, high ice content here, this will create a problem on the long run. And it's difficult to engineer this away. This is the important thing because this is now a climate-driven change. So, well, my take-home message is basically, I hope we can support you with our climate modeling. Please understand that this is not individual elements of a road, not individual infrastructure. We take the picture always from a very, very far away outside picture, bird's eye view on the Arctic. But we can maybe help you with testing certain warming scenarios and testing also certain designs in terms of the vulnerability towards climate warming. That is the intention. I hope we can do something in that direction and combine a little bit the engineering and the climate change perspective. So thanks a lot.